So in our previous classes, we discussed about how an argument or the validity of an argument can be checked using the standard implications and equivalence of primitive logical statements. Now, we are going to go through or discuss some examples in which we test the validity of some arguments. So let's start with a simple one. Here we have a number of premises. Here P, Q, R, S are primitive statements, and we have uh, the premises P then Q, Q then R and S, negation R or negation T or U, P and T. These are the premises. So here these are premises, and we have the conclusion. Therefore, U is the conclusion. This is our conclusion. And now we have to check whether this argument is valid or not. So at first, when we see all these expressions, we cannot make any conclusion or make check whether it is true or the argument is valid or not. So we have to check the validity of this argument in a systematic step-by-step procedure. So what we are going to do uh, is to check whether we can arrive at the conclusion U from the premises in a systematic step-by-step procedure or not, or if we follow such a procedure, whether we arrive at contradiction to our conclusion or not. So we just start with the premises, and we are going to apply the non-equivalences of logical implications, and whether we can arrive at the conclusion or not. So first, we start with the given premises. So we start with the one P implies Q. So that's actually our premises. Then the second one, uh, Q implies R or S. That's again another premise. Now from this first and two, it is P implies Q. Then second one is Q implies R. So we can conclude that P implies R or S. So this is a logical argument. P implies Q, then Q implies R, then P implies R. So that is the logical implication, which is known as logical syllogism. So it is 1 and 2 and the logical syllogism. So actually what we are giving here is our arguments and the reason behind the arguments. So the first one, here we place our arguments. This is merely a street step number, and we give the reason. So this is by the logical syllogism, and by the steps 1 and 2 we can argue that P implies R and S. Now the fourth step, uh, here we have P and T. That is again given condition. Here it is given that P and T is true. So that's again from our premise. Then if P and T is true, then we can conclude that P is true. Obviously P and T is true only when P is true as well as T is true. So we can conclude that P is true, and also we can conclude that T is true. Anyway, for the time being we just concentrate on P, and the rule we used here is the simplification from uh, disjunctive, okay, it is conjunctive simplification. So this is conjunctive simplification. That's a reason. Anyway, so it is P. So if P is true, then P implies R and S. So obviously R and S is true. So that is if P implies Q, and if P is true, then uh, the conclusion is true. That is our modus tollens, the first one. So that is R and S. So we arrive at the conclusion that R and S is true. Now, here we have the premise, uh, seventh one, negation R or negation T or U. So that's again our premises. Then uh, from 6 we can conclude that R is true, because R and S is true. R is true. That is a simplification from uh, conjunction. So it is conjunctive simplification, and it is obtained from the statement 6. So 6 and conjunctive simplification. And now next step, since R is true, negation R is false. So from 7 and 8, if we combine those two statements, then obviously negation T or U is true. This is obtained from the fact that P or Q and negation P implies Q. That statement is that is our, what we call it is distinctive syllogism. So it is distinctive syllogism. So from the statement 7 and 8, and using the implication of distinctive syllogism, we can conclude that negation T or U. Now if you look at our statement number 4, then we have P and T. So just if you combine the statement number 4, P and T, so obviously T is true. For and this conjunctive simplification, we have T. So if we combine these two statements, 9 and we combine 9 and 10, and disjunctive syllogism, we can conclude that U is true. So that's our 11th step. So we start with our premises, and through a step-by-step procedure, we arrive at the conclusion that U is true. So we start from here. We use our premises and a number of valid arguments, and we arrive at the conclusion that U is true. So our argument, the given argument, is a valid argument. So this is the method by which we check the validity of an argument. So there may be different method or different steps through which we can arrive at the same conclusion, but the things which we have to observe or which we have to follow is that we start from the premises, and we are supposed to use the valid logical implication to develop from our premises. And what we are going to prove is that, or what we have to um, develop is a step-by-step procedure which end up in our conclusion. So this is one example, and let us have another example. So here a statement is given: if a band could not play the rock music on, or the refreshment were not delivered on time, then the New Year's party would have been cancelled and Alicia would have been angry. If the party was cancelled, then refunds would have to be made, and no refunds were made, and therefore the band could play the rock music. So we have to check whether the final conclusion, the band could play the music. This is our conclusion, and whether this conclusion is logically obtained from our set of premises. So here we have a number of premises. First step, we have to rewrite all the premises in terms of primitive statements. So let us start with identifying the primitive statements from the premises. First one, if the band could not play the rock music, so the band uh, play the music or rock music. That's our first premise. Then second one, or the refreshments were not delivered on time. So refreshment delivered on time is our second premises. So it's better to write our premises in positive sense, and if our statements contains negative sense terms, so that can be written as negation P or negation Q. So write down the statements, primitive statements, as positive statements. So this second statement, the refreshments were delivered on time. The refreshments delivered on time. That's our second statement. Then the third one, uh, if the refreshment not delivered on time, then the New Year's party would have been cancelled. The New Year's party is cancelled. That is R. Then there is one more thing. Alicia would have been angry. So that is our next statement. Alicia would have been angry. So he was, she was, or he was, she was. Okay, she was angry. Then the third one, T. Uh, if the party were cancelled, that is our statement R, New Year's party was cancelled, then the refunds would have to be made. Also, refunds were made. That's the statement. Then no refunds were made is the negation of T. Then therefore the band would play rock music. That is our conclusion. The band play the rock music. Okay, that statement is already written here. P. Now these are the primitive statements included in our premises, and the conclusion is also written in terms of the primitive statement. It is already identified. Now, what is our next step? We have to rewrite the premises in terms of the primitive statements, and The first one, if the band could not play the rock music, that is negation P, band could not play the music, and if the refreshments are not arrived in time, then two things happen. This implies one thing is the New Year party is cancelled, that is R, and second thing, the Alicia would have been angry, so R and S. So that's our first uh, sentence. If the band could not play the rock music or the refreshment not delivered on time, then the New Year's party would have been cancelled and Alicia would have been angry. That is expressed as negation P and negation Q implies R and S. Then the second statement, if the party were cancelled, that is R, if the party were cancelled, then what happens? Uh, then refunds would have to be made. So that is, uh, then your party is cancelled, that is R. If R is happened, then refunds would have made. So the R implies T. Now, anything else? No refunds were made. So it is negation T. So these are the premises, and our conclusion is that New Year party, the band performed. Therefore, the band could play the rock music. The band play the rock music. That is our primitive statement P. So we have three premises and one conclusion, and we have to check whether this is a valid argument or not. So we start with a simple premise. R implies T. So obviously it is our premises. Then second one is negation T. Negation T is again our premise. Then third step, okay, here if P implies Q and negation Q, then we can conclude that negation P, or in other words, P implies Q and negation Q implies negation P is two equivalent statements, or this argument P implies Q, the negation Q is negation P is known as modus tollens, and by that argument we can conclude that negation R. So that is by 1, 2, and the logical implication of modus tollens. Now, so that means negation R is true. Now, what we have done, if we have negation R, then negation R or negation S is true. That means if P is true, then P or S is true, or P or Q is true. That can be written in logical term as something like P. Then you can conclude that P or S. If P is true, then we can conclude that P or S. That is distinctive amplification. So using that argument here, 3 and distinctive amplification, if we combine those two arguments, then we can rewrite as negation R or negation S, then negation R or negation S is equivalent to negation of R and S. This is nothing but our De Morgan's law. Negation of R and S is equal to negation R or negation S. Now look at our first premise. It is negation P and negation Q implies R and S. So that is our next step. We have the premise negation P and not and negation P or negation Q implies R and S. So that's again our premise. Then if we combine this premise uh, with the fifth one, the sixth premise, and if we use the fifth step, negation of R and S is true. So obviously the negation of P or negation Q, the or negation is true. That is again by our the argument of modest tolerance. Modest tolerance, that is P implies Q, then negation Q implies negation P. So that is again using the De Morgan's law. If we rewrite it as P and Q, that means again De Morgan's law, and therefore if we have P and Q, then obviously P is true. P and Q is true means P is true. This is by conjunctive simplification and the statement 8. So we arrive at the statement P, and P is nothing that the band play rock music. So that's our conclusion. So this is again a step-by-step procedure to arrive at a conclusion, and the difference from the previous question or previous problem is that here we are dealing with a number of perfect arguments or a literature or a literate argument in form of common English, and we transform the statements into primitive statements and establish or express our arguments in terms of uh, primitive arguments using logical connectives and logical statements, and then from that statements we use the logical implications to arrive at our conclusion, and after arriving at the conclusion we just go back to our statement in common language. So that is how we prove the validity of this particular statement. And now let us have one more example. So let us consider the premises. Negation P if and only if Q, that's one premise, and then next one, Q implies R, then negation R, and our conclusion is P. So we have to check whether this argument is a valid argument or not. So here Anyway, first we can start with the simplest argument, which is given negation R. It is our premise. Then second step, if we have negation R, then obviously negation Q is true, because okay, we have the premise P then Q. Q implies R is our premise, and then we can have negation R is combined with Q then R. Then as in the previous case, we can have negation Q. That is again by the modus tollens and using the arguments 2 and 1. Now, so negation Q is there. Now what we have here is negation P if and only if Q. Negation P if and only if Q. That is again our premise. Now we are going to use a tricky method. Here we have looking for the conclusion that P is true. So we just assume that P is not true. So this is our assumption, not a premise. It's an assumption, and we assume that negation of our conclusion. This is our negation of our conclusion. Negation P. So we have negation P and negation Q. Now here we have the 6. Okay. Negation P implies and implied by Q can be written as negation P implies Q and negation Q implies negation P. Therefore we can simplify or write as negation P implies Q. So we assume negation P, and therefore we can conclude that Q. So here we get Q is true, and if Q is true, using our premises 2, Q implies R, so we can have R using the step 2, and from step 9 and if we use step 9 and we have okay, if we use our first premise, that is negation R, so step and 9 and 1, then we can conclude that R and negation R and negation R. So here we get R, and in the first step we start with negation R. So here starting premise is negation R. So we arrive at a step in which we have R and negation R. Obviously R and negation R is a contradiction, so it is always false, but our systematic argument arrive at a conclusion that that which is a contradiction, and we arrive at this particular contradiction only because we make an assumption here in our first step number 5 negation P, and a contradiction is a result of our assumption negation P here, and therefore that assumption is wrong. All the other things are given in our premises, and the premises is always true, and all the rules which we use in our logical arguments are valid rules, and therefore they cannot be wrong. So the only thing which is wrong and which leads to our contradiction is our assumption that negation P, and therefore we can conclude that our assumption is wrong and P is true. And this is a strong method which we use to prove many of our results in mathematics, and this method is known as uh, proof by contradiction. Proof by contradiction. So in proof by contradiction, what we are doing is we assume the converse of our conclusion together with the given premises, and if that argument leads to a contradiction, then our assumption that the converse of the conclusion is true is wrong, and therefore the conclusion is a valid argument from the given premises. So that is how we uh, use the technology of proof by contradiction in proving many results. So this simple argument is used while proving many mathematical results. So, for example, uh, if we have a result which says uh, there are uh, infinitely many uh, prime numbers. This is a simple result in mathematics, and the logical argument which we use to prove this result is uh, as follows. We start with if possible, let there are only a finite number of primes. So this is our assumption, uh, and if you observe this statement, it is nothing but the converse of or the negation of our theorem. So if the theorem is P, then we start with assuming the negation. Now we develop a logical sequence of arguments from the negation P, like if there is only a finite number of prime numbers, then we can name them as P1, P2, P3, etc., Pn, and then let it be the uh, primes. So we assume that there is only a finite number of primes, and if there is only a finite number of primes, then we can name them as P1, P2, etc., Pn, and we construct a new number, say Q is equal to, so Q is equal to P1 into P2 into etc. Pn, then plus 1. So P1, P2, etc. Pn are integers because they are prime numbers, positive integers. Then we can take the product of them. There is nothing wrong in that. Then taking the product of n integers give rise to a new integer, and the new integer plus 1 is another integer, and that integer is named as q. So here we get an integer q is equal to p1, p2, etc., pn plus 1. And if you observe closely this particular integer q, then q is not divisible by any of the numbers or any of the prime numbers we already named, or if we divide q by p1, then it is p2 into p3 into etc. pn plus 1 by p1, and there is a fraction and it is not uh, divisible by p1, and in a similar way q is not divisible by p2, it is not divisible by p3, etc. It's not divisible by any of the prime numbers we already enlisted in our set of prime numbers, a finite set of prime numbers. So q is a new prime number, and so we can make this conclusion: q is a prime, and q does not equal to pi for any I. So we assume that p1, p2, etc. pn be the set of all prime numbers, and we arrive at a new number which is prime and which does not belongs to the set. So this is actually a contradiction to the assumption that there are only a finite number of prime numbers, and that prime numbers is listed as a sequence p1, p2, etc. pn, and we are arrived at a new prime number which is not present in that sequence. So that's a contradiction, and that contradiction is due to our assumption that negation p, if possible there be a finite number of prime numbers. That assumption is wrong. So therefore we can conclude that p is true, that is there are infinitely many prime numbers. So this is how we use the method of proof by contradiction in our practical situations. So this is the so in this lecture or in this session we come across a number of cases in which we check the validity of an argument using the method of logical implications and um, basic rules of logics. So this is how we have to check the validity of any arguments in uh, logics. So by this we wind up our session today, and we will meet again with the discussions on existential quantifiers, universal quantifiers, etc. That's a different section of fundamentals of